What is something that you do every single day? You do it before you go to work. You do it before you leave your house. You do it even before you put on your shoes. You put on your socks. Have you ever wondered, how do the socks get there? Companies like Crystal AG manufacture the socks you wear every day. Once the socks have been made, they need to be packaged, labeled, and sealed before they are shipped. Right now, it is a costly, labor-intensive process that takes hundreds of people and thousands of hours to complete. With the current methods, Crystal AG can't compete with the cheaper Asian labor and will likely need to shut down their plant. Now, what if there was a machine that could assist in this process? Our group is devising a method to greatly reduce the human labor needed to produce these socks while doubling the output of the facility. We are using innovative solutions that have never been used in the sock manufacturing industry to create a machine at a fraction of the cost of similar machines in other industries. Ideally, this machine will save the facility from shutting down, saving countless jobs.
Introducing Megatronix design to solve the sock packaging problem. Before the packaging process can begin, bags must be loaded into the system. The bags used for this process come in horizontal stacks of around 100 bags. To keep them, the bottom of the enclosure is spring-loaded. To place the bags into the system, all that an operator must do is press down on the bottom of the enclosure and slide the bags in. Once the bags are in place, the springs press them gently into the roller mounted using the bearings on each side of the box. Once the bags have been loaded, the system can begin. The first step in the process is to isolate a single bag off the top of the stack of bags. To do this, the roller that the bags are pressed into is motorized. The springs beneath the enclosure platform press the bags upwards with a force that causes only the top bag to be rolled forward. Here, we can see the prototype we created successfully dispensing a bag. One limitation this prototype has is that the springs being used are repurposed and therefore an approximation of the correct spring constant. Even so, the system was exceptionally reliable, with around a 95% success rate. After a bag leaves the enclosure, it travels through a second set of rollers, one of which is motorized. A blower is mounted above the second set of rollers, which blows downwards and ensures that the bag falls into the slide as it is dispensed. The bag will continue to be dispensed down the slide until it reaches the slot, about 3/4 of the way down the slide. An ultrasonic sensor mounted in this slot signals for the motors to stop, at which point only the very end of the bag will be held by the second set of the rollers. The rollers pinch the bag with enough force to hold it in place as the sock is placed into it. Here we can see that this system works in practice. The bag is sent down the slide and held only by the very end of the bag after being dispensed. Like the dispensing system, this system also works extremely consistently. Now that the bag is held in place, a sock can be placed in it. Before this can happen, the bag must be opened. To do this, a blower is used to shoot compressed air into the opening of the bag, causing it to inflate. Once the bag has been opened, a conveyor on top of the machine begins running. This conveyor has a sock loaded onto it, which is dropped off the conveyor through a chute into the open bag. The opening blowers are positioned on the sides of the chute to avoid the sock blocking the compressed airstream. After a sock is loaded, the bag falls onto the slide into a conveyor. The bag falls so that almost the entire bag leaves the slide, but the end of the bag remains on the ledge of the slide. The bottom conveyor belt then runs, which causes the flap of the bag to be caught on the ledge and to fold over the rest of the bag. The bag then travels under a curved surface, which has been determined through testing to provide the most reliable folding behavior. To ensure the tape seals the bag properly, a piston and roller are used. After the tape has been caught by the bag, a piston is actuating, pressing the tape firmly into the bag. This ensures that the tape is actually stuck onto the bag. The bag then goes under a large roller with a soft outer surface to uniformly stick the tape to the bag. After the bag has been folded, it is conveyed under a taping mechanism. An automatic taper dispenses a piece of tape which hangs over the conveyor with the sticky side facing the bag. As the bag rolls through the hanging tape, it catches the tape and pulls it off the automatic taper. Now that we've gone through all the sub-functions, let's see them all working together. Overall, this system solves the problem of automating the sock packaging process. It would eliminate the need for a worker to bag socks, but an operator would still be required to load bags and ensure that the system is running smoothly. This system produces a packaged sock in 4 seconds, which is under the sponsor's time requirement of 4.5 seconds. It is reliable, with failures only ever occurring within the taping mechanism, specifically due to jams. However, manual operation of the piston through one of the buttons allows an operator to fix this issue as it occurs. The product is 10% the cost of competitors and functions with the same throughput speed. Cost reduction would be made possible by minimizing moving parts with innovative geometric solutions. Inspirations for these solutions were taken directly from printers, playgrounds, and food packaging. Mechatronic's packaging system is also unique compared to the industry standard, as bags are folded and taped instead of heat sealed. This enables cost-sensitive companies to effectively switch to recycled bags, reducing the pollution to the environment.
Come to the Georgia Tech Design Expo December 2nd at the McCamish Pavilion to see the future of sock packaging.